Today we're going to learn a little bit about the actual calculations with our combined gas law. We learned about pressure, volume, temperature, and number of moles as variables that are going to be included in these types of problems. And then we're going to do one of each. So the first one says it's a Boyle's law problem, but let's go through how we would know that, even if it wasn't labeled as a Boyle's law problem. It reads, a sample of argon can be used in a sign that has a volume of 1.51 liters at a pressure of 635 torr. What is the new volume after it's pumped into a glass tube that has a pressure of 785 torr? So my initial conditions will have a initial volume of 1.51, initial pressure of 635 torr. Now, torr is a unit that means the same thing as millimeters of mercury. The new pressure is going to be 785 torr, and they're asking us to solve for the new volume. Now, we figure out what our formula is, and remember, if you write down the combined gas law, which is P1V1 over T1 equals P2V2 over T2, this one does not contain temperature. So all you're going to do is write down the temperature stays constant so that we can cancel out both of them from each side. And my formula becomes P1V1 equals P2V2. I'm going to rearrange this formula to solve for V2. How I get V2 by itself is to divide each side by P2. That cancels these out, and my formula becomes V2 equals P1V1 over P2. So let's plug in our numbers now. So P1 is 635 torr. I'm going to use my units in here because if I use my units in my rearranged equation, it will tell me if I've made a mistake. And then 785 torr on the bottom. So you can see that the torr is going to cancel out, and I'm left with liters, units of liters on the top. If units of liters were on the bottom, have that be a red flag that you've made a mistake. Either you rearranged incorrectly or put the numbers in the wrong spot. And I get a long answer for V2 of 1.2214649668. But we only need sig figs of 2. We need 3 sig figs here. So 1.22 is going to be my answer. Now let's talk about if this is reasonable. Because the pressure went up and these are multiplied in the equation, therefore they're inversely related, we expect the volume to go down. That's the good thing about problems like this. If you've done it incorrectly, the pattern will not match. So if your pressure goes up and your volume also goes up, you know you've made a mistake. So that's going to be a good way to check yourself. Next one is a Charles law problem. A child's balloon has a volume of 3.00 liters when it's indoors at a temperature of 18 degrees Celsius. Find its volume outside where the temperature is 36 degrees Celsius. So V1 is 3.00 liters and T1 is 18.0 degrees Celsius. I'm going to right away turn that into Kelvin. Remember, all of my temperatures have to be in Kelvin. Find its volume outside where the temperature is 36 degrees Celsius. Also change that right to Kelvin. And we're going to find the new volume. So if you look up at our combined gas law, you're simply going to write it down without pressure. So it'll be V1 over T1 equals V2 over T2. So our temperatures that we've calculated, we're not even going to use Celsius at all, is 291 K. And 309 K. So because, let's write this down, V1 over T1 equals V2 over T2. We're solving for V2. Because this is a divided by, this is a direct relationship. So temperature went up, we expect for volume to go up. Let's get V2 by itself. We'll multiply each side by T2. Cancel these out, and my formula becomes T2 equals V1 T2 over T1. Now we'll plug in our numbers with units, and you'll see that my temperature units of Kelvin will cancel out, and I'll be left with liters on the top, which is what I'm looking for. Let's cancel these out. And my calculator tells me 3.185567001. We're again in 3 sig figs, so it's going to be 3.19 liters. So the temperature went up, so did the volume. That makes sense. Next one is a Gay-Lussac problem. A tire is inflated to 301.0 psi of pressure on a cold day when the temperature is 0 degrees Celsius. Assume no air escapes and the volume doesn't change. What will the pressure be when the temperature reaches 40 degrees Celsius on a hot summer day? So we're going to look at our combined gas law, and we're going to say that the volume doesn't change. So it's going to become P1 over T1 equals P2 over T2. So let's write down what we have here. The pressure, this unit is PSI. PSI is pounds per square inch, and the conversion factor is 14.9 pounds per square inch is equal to 1 atmosphere. The temperature here is 0 degrees Celsius, which is, add 273 is 273 K. What will the pressure be when it reaches a temperature of 40 degrees Celsius on a hot summer day? Which is 313 K. So let's write our formula down. P1 over T1 equals P2 over T2. We can also think about just bringing T2 to the other side by bringing them up to the top. So my formula becomes P2 equals P1 T2 over T1. Plug in my numbers with units. 301.0 PSI times 313K over 273K. My K's cancel. I'm going to get left with units of PSI, which is fine. That's what the problem gave us. And I'll get an answer of 345 to 3 sig figs PSI. Let's say you wanted to know how much that was in atmospheres. The equivalency statement is there's 14.9 psi is equal to 1 atmosphere. So if I wanted to convert this, when we do these conversion factors, you want to cancel psi, so psi goes on the bottom. What you want to change it to goes on the top. They stay with the numbers in the conversion factor, so atmospheres always gets a 1, and psi always gets a 14.9. So if I wanted to know what this was in atmospheres, it is 23.2 atm. Standard is 1 atmosphere, so that's a high pressure in a tire, which is exactly what we expect to see. The combined gas law problems. Next one says a gas has a volume of, let's start writing these down right away, 20 liters, a temperature of 100.0 degrees Celsius. Let's go ahead and add 273 right away, and a pressure of 720 millimeters of mercury. What is the new volume at STP? Now, STP stands for standard temperature and pressure. So that's actually a number. It's actually a given. So you can look this up, but it stands for standard temperature and pressure. And the standard temperature, or T2, is going to be 0 degrees Celsius, or 273 K. The standard pressure, which is going to be P2, is going to be 760 millimeters of mercury. That's my conversion factor. So the numbers are going to be the same. So let's take our whole formula of P1V1 over T1 equals P2V2 over T2. Let's bring this guy up, and let's bring this guy down. And my formula becomes V2 equals P1V1 T2 over T1 P2. Let's plug some numbers in with units. 720 millimeters of mercury, 20 liters, T2 is 273 K. And then on the bottom, we have T1, which was 100 degrees Celsius, or 373 K. And P2, which is 760 millimeters of mercury. Now let's check our units. Cancel, 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 cancel. We end up with liters on the top, which is what we're looking for. So 720 times 20 times 273, and then I push enter, divided by parentheses 373 times 760. You should be doing this in your calculator too. We're going to have 3 significant figures in this answer. So my calculator says 13.8676. So I'm going to round it up to 13.9 liters. Remember, our rounding rules are the same as they were in math class. One more of the combined gas law. A fire extinguisher contains 500 milliliters, so that's V1, of CO2 at a temperature of 20.0 degrees Celsius. Add 273 to change it to Kelvin. And 40 atmospheres of pressure. That's highly pressurized, which is what we would expect for a fire extinguisher. It is released. When it released, the gas expands to a volume of 15,000 milliliters and a new pressure of 1.0 atmospheres. What's the new temperature in Kelvin? Now, this is tricky here because we're going to rearrange the equation, but we can't just start moving stuff around, because what we're going to end up having is, if we try to get T2 by itself, it is going to end up on the bottom, and you don't want to solve for T2 on the bottom because it'll be the inverse of the number. So here's a little trick. If you want to solve for a number on the bottom, you can flip it, because if P1V1 over T1 equals P2V2 over T2, it also means that T1 over P1V1 equals T2 over P2V2. Now I can just take P2 and V2, multiply each side by P2 and V2, they'll cancel, or think about it bringing it up to the other side, like this. This will allow me to solve for T2 on the top. If you get units of K on the bottom, that's exactly what you've done. That's the mistake you've made. So P2 is 1 atmosphere. V2, 15,000 milliliters. And T1 is 273 plus 20, or 293 K. And all of that's going to be over P1, our high pressure of 40 atmospheres, and V1, which is 500 milliliters. Let's check our units. Milliliters cancels with milliliters. Atmospheres cancels with atmospheres. You're left with units of K on the top is what you need. If you get K on the bottom, you've rearranged incorrectly. So have that be your red flag to tell you you need to go back through and check your work. So now I'm going to multiply across the top. So it's 15,000 times 293 and divided by parentheses 40 times 500.0. And I get an answer of 219.75 K. If we were going to round to 3 sig figs, that would be 220 K. If you want to know what that is in Celsius, all you have to do is subtract 273 from that. And I always use my raw answers. So it'd be 273 minus 219.75 for negative 53.25. To 3 sig figs, it's negative 53.3, which is very cold. So next we will be going to the ideal gas law, and I will have another video for you to watch in class.